Hello, welcome to this lecture. So in this lecture, we will be learning about the classification of orientation preserving isometries of hyperbolic plane. For instance, so if I take the upper half plane model of this hyperbolic plane, so we know that PSL to R, it acts as an orientation preserving isometric group on the upper half plane. So given an element of this PSL to R, so depending upon the fixed points of that isometry, will be classifying that isometry. So let us begin. Let us take the upper half plane model of this hyperbolic plane. Let us take this upper half plane model of this hyperbolic plane. So on this H2, we have this hyperbolic metric. ds square is equal to dx square plus dy square by y square. And we know that, so the group PSL to R, it acts on this upper half plane, and the action is by orientation preserving isometries. Okay, so now if I take any element tz in this PSL to R, so this T, it belongs to your PSL to R. So this means that, so this A, B, C, E, so these are my real numbers, and AD minus BC is not equal to your, sorry, AD minus BC is equal to your 1. So we'll also take, so let us take, so this T to be non-identity element of this PSL to R. So we'll be first interested in the fixed points of this TZ. So in order to get the fixed points of this TZ, so we'll have this equation. So fixed points of TZ is this set. So Z belongs to C such that TZ is equal to Z. So now if I look into this equation, TZ equals to Z. So this will give me the following quadratic equation. So AZ square plus D minus A times Z minus B is equal to your 0. So CZ square plus D minus A times Z minus B is equal to your 0. So we have this quadratic equation. So now case 1. So suppose C is equals to 0. So if C is equal to 0, so then, so TZ is of this form, A by dz plus B by D. And because this AD minus BC is equal to 1 and C is equal to 0, so we have this AD is equal to your 1. And now suppose, so mod of A is greater than 1. So this will imply that fixed points of TZ are B by D minus A and infinity. Yeah, so this is coming from this equation, this quadratic equation. So this is coming from this quadratic equation. So B by D minus A, so this will be a fixed point. So you're putting C equals to 0 here. And because this mod of A is greater than 1, so also you have this infinity also as a fixed point. Yeah, so yeah, sorry. So mod of A, if it is greater than 1, so if suppose A is equal to 1, so then D will be exact also equal to 1. So then D minus A is equal to 0. So mod of A greater than 1, it implies that D is not equal to A. So therefore, so B by D minus A, it makes sense. So it is again a complex number. So therefore, fixed points of TZ are B by D minus A and infinity. Okay. And now also observe that, so we have put C equals to 0. So therefore, so the matrix A, B, C, D, it is this matrix. So A, B, 0, and T is equal to, AT is equal to 1. So T is equal to 1 by A. So therefore, so trace of this matrix, so this is equal to your A plus 1 by A. So this is always greater than your 2. Yeah. So here I should put mod here. So mod of this trace of this matrix, so which is equals to mod of this A plus 1 by A. So because this mod of A, I have taken it to be greater than 1. So it turns out to be that mod of this A plus 1 by A, it is greater than your 2. So we have this observation here. And in the next case, suppose mod of A is equal to 1. So we already assumed that the C is equal to 0. So Tz is equal to your A by dz plus B by D. And we also have this AD is equal to your 1. So from here, so what will follow that? So mod of, so A is also a real number. So mod of A is equal to 1. So A is just plus minus 1. And AD equals to 1. It means, it implies that if A is equal to minus 1, so D will be also minus 1. So therefore, so this will imply that, so A is equal to D. So therefore, so this Tz, so this will be of this form. So Z plus B by D. And also note that this T is not equal to identity. So T is not equal to identity implies B by D is not equal to 0. So therefore what we have, so T is just a translation. So T of infinity is equal to your infinity. So fixed point of T is just the singleton set infinity. And now uh, we have this case 2 where the C is not equal to 0. So let C not equal to 0. So in case 1, we have assumed that C is equal to 0. And in the case 2, let us assume that C is not equal to 0. And so we have this also, this quadratic equation, CZ square plus D minus A times Z minus B is equal to 0. So we have this equation here. So what is the discriminant? So discriminant is D is equal to your D minus A whole square plus 4BC. So this is nothing but equal to your A plus D whole square minus 4 times AD minus BC. And we know that AD minus BC is equal to 1. So what we have, A plus D whole square minus 4. And the mod of the trace of this matrix, so this is AB, this matrix is ABCD. So this is mod of A plus D. So therefore what we have, so now again the subcase A. So if I assume this mod of A plus D is greater than 2, so the discriminant will be greater than 0. So D greater than 0. So this will imply that, so this quadratic equation has exactly 2 roots in R. Okay, so that will imply that, so T has exactly 2 fixed points on R. And the second subcase is, let us assume that this mod of A plus D is equal to your 2. So this will show that the quadratic equation, so this quadratic equation, it has 2 equal real roots. So therefore what we'll have, uh, so T has exactly 1 fixed point on R. And now the third subcase, let us assume that mod of a plus t is less than 2. So then this quadratic equation, so t will be less than 0. So this will imply that the quadratic equation, so this quadratic equation, star quadratic equation, it will have two imaginary roots. So it will have two imaginary roots. So, and the roots will be conjugate to each other. So one root will lie in the upper half plane and the other root will lie in the lower half plane. So that will imply that, so in the upper half plane only you have only one root is there. So therefore, so the conclusion is T has exactly one fixed point in the upper half plane. Okay, so now let us work with some examples. So for example, if I take dz to be equal to your lambda z, where this lambda is not equal to your 1, or you can take lambda to be greater than 1. So if I think about this matrix, root lambda 0, 0, 1 by root lambda. So this belongs to your PSL to R. And if I take this map, lambda z, root lambda z plus 0 by 0 z plus 1 by root lambda. So this will be exactly equals to your lambda z. So Tz is equal to, so the action of this matrix on the upper half plane. So fixed point of this T is equal to your 0 infinity. And of course, so mod of trace of this matrix, so this is greater than 2. So second example is, so Tz equals to z plus b, where this b is a non-zero real number. So T of infinity is equal to your infinity. So fixed point of T is just this infinity, singleton set infinity. And the third example is, so Tz equals to your cos theta z plus sine theta divided by minus sine theta z plus cos theta. So in this case, so the fixed point of this T is the singleton set I. Okay, so now let me define this thing. So definition. So types of isometries. So let T be an orientation preserving isometry of this upper half plane. So which is exactly, this group is exactly equal to your PSL to R. And let us take T not to be equal to identity. So we say, so T is said to be a hyperbolic isometry. So T is said to be hyperbolic. So if T fixes exactly 2 points on this R union infinity. Second is T is said to be parabolic. So T is said to be parabolic. So if T fixes exactly one point on R union infinity. And the third is T is said to be elliptic. So if T fixes a single point in the upper half plane. So here you will not get the boundary of this upper half plane. Okay, so yeah, so this is about the types of isometries of this upper half plane. So observe that. So T is hyperbolic from the above, from the previous thing. So what we have? So the trace of the matrix. So it will be mod of the trace of the matrix. It is greater than true, and T is parabolic if and only if mod of the trace of the matrix is equal to true, and T is elliptic if the mod of the trace of the matrix is less than 2. So next we'll learn about the axis of hyperbolic isometry. So again, let us take T to be an orientation preserving isometry of this upper half plane. And let us assume this T to be an hyperbolic isometry. So let T be a hyperbolic isometry. So this means that, so this T fixes exactly 2 points on R union infinity. So let us take, so this fixed point of T to be equal to the set T minus and T plus. So this 2 points T minus and T plus, so this belongs to your R union infinity. So now what you do, so join T minus and T plus by a by infinite geodesic A of this upper half plane. So this A will be called the axis of T. So A is called the axis of T. So this is the definition of axis. So if I draw a picture, so this is my upper half plane. And now suppose, so this is the geodesic. Oh, sorry. So you have an isometric tree, and this T minus and T plus, it belongs to your R. So then what you do, you just join these 2 points by a by infinite geodesic. So this by infinite geodesic, so this has been named A. So this A is the axis of this hyperbolic isometric T. Now if one of this T minus or T plus, if it becomes infinity, so then you have this picture. So you have this vertical axis. This my T minus and T plus here is equal to your infinity. And this A, it is my axis of this isometry T. So now the claim is So A is invariant under the action of T. That is, so T fixes this axis setwise. So T of A is equal to your A. So the proof is very simple. So what is the proof? So we know that the fixed points of this T, so these are my T minus and T plus. So therefore T of T minus is T minus and T of T plus, so this is your T plus. So A is the geodesic joining T minus and T plus. So this upper half plane, it is a unique geodesic space. So we have, so this geodesic, so this is a unique geodesic joining T minus and T plus. Now also note that T is an isometry and T fixes T minus and T plus. So this should be your T plus. So TA is again a geodesic, is a geodesic joining T of T minus and T of T plus. And T of T minus is exactly equal to your T minus and this is exactly equal to your T plus. And because it is a unique geodesic space, so T of A has to be equal to your A, as the upper half plane is a unique geodesic space. So now let us do this observation. So we have this following observation. So let us take an orientation preserving isometry. So it will belong to your PSL2R and let us take this T is not equals to entity. So we have this following observation. So let us call it observation 1. So let us take T to be a hyperbolic isometry. So claim is, so there exists an isometry, orientation preserving isometry, or S belongs to your PSL2R, such that, so ST S inverse Z is equal to your lambda Z. For some lambda not equals to your 1. So you can think in terms of linear algebra also. So corresponding to 2, you have a 2 by 2 matrix ABCD, where the, ABCD it belongs to your R and AD minus BC is equal to 1. So it says that, so that matrix can be diagonalizable in this context. So we have a geometric proof of that thing here. So we have taken this T to be a hyperbolic isometry. So fixed point of T, so this will be just 2 points, 2 distinct points in R union infinity. So we can draw this picture here. So this is this is my upper half plane, and suppose T minus and T plus, it lie on the real axis. So the axis of this hyperbolic isometry, I have taken it to be A. So A is a geodesic joining T minus and T plus. And now let us take the imaginary axis. So this is my imaginary axis. And now what do we know? So there exists a Mobius transformation. In fact, there exists an element of this PSL to R which takes this geodesic A to this imaginary axis. So there exists S belongs to your PSL to R, which will take this geodesic A to your this imaginary axis. Let us call it to be capital I. So there exists S belongs to your PSL to R such that S of t minus is equal to your 0, S of t plus is equal to your infinity. So this will imply that S of A is equal to your this imaginary axis I. So now if I take this conjugate ST S inverse and you apply it on the imaginary axis I, so S inverse I is A because S of A is equal to I. T of A is equal to A. So we have here SA, so which is again equal to I. So this conjugate, again it belongs to your PSL to R and it fixes the imaginary axis I. So this will imply that so this map STS inverse of Z, so this will be equal to lambda Z for some lambda not equal to your 1. Yeah, so you can check this thing. Okay. And the next observation is, so now let us take T to be a parabolic isometry. So then there exists S belongs to your PSL to R such that STS inverse Z is equal to your Z plus B for some B not equal to 0 and B belongs to R. So this I leave as an exercise, and third one also I leave as an exercise, can discuss in it in some tutorial. So any elliptic isometry is conjugate to this map. So this also I leave as an exercise. Yeah. So this observations will be very useful in the later classes. So we'll see. Okay. So I'll stop here.